Hello, grade 12s. Welcome back to this channel. Today, I want us to look at the fundamental accounting principle from Kevin Smith study guide. Okay, so the fundamental accounting principle from Kevin Smith study guide. So this is the definition of fundamental accounting principle. Let me just highlight it here. So here's it. So the fundamental accounting principle, it's a principle that is used to determine the number of different ways to accomplish different tasks, right? So it states that if there are m ways to perform a task and n ways to perform a second task, then the total number of different ways in which we can perform both tasks, it's m multiplied by n. So take a look at the mathematical representation of the fundamental accounting principle according to Kevin Smith. So he says this principle really helps us to determine the total number of different ways in which we can accomplish different tasks, right? So if a certain task can be accomplished in m ways and another task can be accomplished in n ways, then in order to determine the total number of ways in which you can perform both tasks, we simply multiply those number of ways in which we performed each of the tasks. Then we get the total number of ways in which you can perform both tasks. Okay, I like the example one that Kevin Smith used here. He sort of used a practical example, and by saying a local cafe has 4 different flavors of ice cream with a choice of 8 different topics. Okay, let me just delete this and just highlight this. So we have 4 different flavors of ice cream, don't forget, and we also have with a choice of 8 different toppings, right? So from those ice cream, we can choose 8 different choice of toppings for dessert. So if a customer chooses one topping and one flavor, how many different choices of dessert are there, right? So this is a practical example and very important first example in counting principle. So using the fundamental accounting principle, we know that there are 4 choices of ice cream flavors, right? And we also know, okay, we have 4 choices of ice cream flavors, and we also know that we have 8 choices of toppings. So we have 8 choices of toppings. So the total number of choices using the fundamental accounting principle, according to the definition, we simply multiply the number of ways in which you can arrange certain tasks in a certain event. Now we are talking about choices, right? So you simply multiply the number of choices that you have for each particular situation. So we had 4 choices of ice cream, then we'll multiply with 8 choices of different topics. Sorry for this. So we'll multiply with 8 choices. Okay, let me just delete this. We're gonna multiply with 8 choices of different topics. So it's gonna be 4 times 8, which will give us in total 24 different choices that this person can choose from. So we know that total number of choices that the person can choose, it's really 24 choices, right? Because you can choose one of the flavor from the 4 ice cream flavors. You can choose one of the topping from the 8 topping together. It's the first choice, like that, like that, like that, up until in total there will be 24 different choices of flavors. Okay, let us look at example 2. Very interesting one also. Okay, it says at a Christmas dinner party, the set menu below shows the choices that patrons have for status. Okay, so we have, these are the choices for status. Let me just use a different color. So these are the choices for status. We have main course and we have a dessert. So how many different meals can be made from the set of menu, right? We want to see if a person is to buy from the status, if a person is to choose also the main course, and if the person is to also say I will also need a dessert, how many different choices of meals that can be made from this set of menu, right? So what you do in counting principle, you simply calculate how many choices do you have in each particular situation. So we're going to start with the status, and we're going to look how many choices are there, right? So we have Greek salad and we have fried calamari rings. So we only have 2 choices in the status. Okay, so let's go to the main course. As you can see, we have skewers of fillet steak served in a mushroom and onion sauce is the first choice, right? And we on the second choice we have fish of the day, lightly pan fried in lemon butter sauce. So it's the second choice. And we also have vegetables last this name. So vegetable what. So how many choices do we have in the main course? We have 3 choices, right? So let's go to the dessert. You can choose ice cream served with hot chocolate sauce, the first choice. Or you can choose a slice of baked cheesecake custard. A slice of baked cheesecake, the second choice, and custard and strawberry third is the third choice. So dessert we have 3 choices. So how many different combinations can be made if a person is to buy in this restaurant offering this set of menu? So we simply multiply the number of choices that we have in each particular situation. So in the status we have 2 choices, in the main we have 3 choices, and in the dessert we have 3 choices. So it's 2 times 3, which is 6, then multiplied by 3, which is 18. So there are 18 different meals that can be made there. So the person can simply make 18 different choices or different combinations if the person is to buy in this store, in this restaurant. Okay, let us take a look at example 3 now. So in example 3, they say a security system requires a user to choose a security code, right? So the code consists of 4 digits. This is very important. The code consists of 4 digits. How many different codes can be chosen if A, the system allows repetition of digits, right? So let us start with that one. If the system allows repetition of digits, how many codes can be chosen? So, or how many codes can be formed? So remember, the system consists of 4 digits. So hence we have 4 spaces there. 1, 2, 3, 4, right? So in fundamental accounting principle, what you have to think of is the number of choices that you have in each particular situation, right? In the first digit, how many choices can you choose from? How many choices of digits can you choose from, right? Remember, they said it consists of 4 digits, right? But we know we have a total of how many digits? We have 0 to 9. We have digits from 0 to 9. So in total, there are 10 digits, right? So it means in the first space there, in the first space, we'll have 10 choices. Do you understand? So because the system allows repetition of digits, look at this statement, the system allows repetition of digits. It means that because you have chosen 10 of the digits, you have chosen any of the digits from 0 to 9, it's 10 of them. It means you can still repeat and use the same digit that you have chosen previously in the second space, right? So it means you still have how many choices? 10 choices. You can either choose any digit from 0 to 9. You can also choose any digit on the third space. You can choose any digit from 0 to 9. On the fourth space, you can choose any digit from 0 to 9. So the total number of different, okay, let me just delete this. The total number of different codes that can be formed. We have 10 choices first position, 10 choices second position, 10 choices third position, 10 choices fourth position. So it will be the multiplication of those number of outcomes or choices that we have in that particular situation. So it's 10 times 10 times 10 times 10, which is 10 exponent 4, which will give us 10,000. So there will be 10,000 codes that can be formed or that can be chosen, right? Okay, B. the system does not allow repetition of digits, right? Remember, we need to form a 4-digit code. Hence, we'll have 4 spaces, 1, 2, 3, 4. But in this case, the system does not allow repetition of digits, right? It means in the first position, you can choose for any digit from 0 to 9. You have 10 choices, hence they put 10, right? We have 10 choices. So in the second position, from those 10 choices, you are only going to use 1 digit, right? From 0 to 9. But remember, in counting principle, we only use the number of choices that we have. Hence, we are saying it's 10 choices. We can't put 1, right? Because although we know we're going to choose one of them, but we are choosing one from how many of them? From 10 of them, right? So in the second position, now, because in your first position, you have already chosen one of the digits from 10 choices, how many choices will you be left with in the second position, right? We have used 1. So in the second position, you'll be left with how many choices? 9 choices. Because one of them has been used and a repetition is not allowed by the system. So we are left with how many choices? 9 choices. So let's go to the third position. 2 of the digits has been used. How many choices are you left with? 8 choices. Then the last position, 3 of the digits has been used. How many choices are you left? 7 choices. So you simply multiply out those number of choices, then you can simply get the answer. Let me quickly use my calculator and see what the answer would be. Okay, we're saying 10 multiplied by 9. We're saying 10 multiplied by 9 multiplied by 8 multiplied by 7. So this will give us 5040 codes that can be formed. Okay, you can complete exercise 2 on page 309 if you have this textbook, or you can actually order it online. It's the online Kevin Smith math handbook. You can purchase it online, I think on Takealot, and some bookstore there. So if you have the book, complete exercise 2 on page 309. Okay, let us now take a look at the factorial notation. The factorial notation. Let me just highlight it there. The factorial notation, right? So, according to Kevin Smith study guide, it says the factorial in brackets, it's something like an exclamation mark, right? So that thing represents a factorial. In maths, we don't call that an exclamation mark, but we call it factorial, right? So he says a factorial of natural number n is the product of positive integers less than or equal to n, right? So this is denoted by n factorial. So, and it's pronounced n factorial, right? I already pronounced it because I know that's what the symbol represents. So if you see something like this, so you simply say this is n factorial, right? It's n factorial. So remember, it's the product of all natural numbers. No natural numbers n of the positive integers that are less than or equal to n. What does it mean? For example, if I have 5 factorial, as the given example here, we had 5 factorial, or we can simply use this one that is given in the book. Look here, we have 5 factorial, right? So it will be equal to is the product of the natural numbers, right? That are positive integers less than or equal to n. So if it's 5 factorial, what is it must be equal to n. So our n here is 5, right? So it will be 5. You decrease the product by 1 because we are saying less than or equal to n. So we're gonna decrease by 1. We go to 4. We decrease by 1. 3. We decrease by 1. 2. We decrease by 1 up until we reach 1. So we multiply those things. It will stand for 5 factorial. With 6 factorial, we do the same. We start with 6 as our n because it's the product of natural numbers n that are less than or equal to n, right? So our n is 6. We start with 6. We decrease by 1. 5. Decrease by 1. 3. 4. 3, 2, 1. Like that. 7 factorial. start with 7, decrease by 1, 6, 5, 4, 3, 2, 1. So if we have n factorial, what does it mean? The product of natural numbers that are of positive integers, obviously, that are less than or equal to n. So we start with n, we decrease by 1. You can see we say n minus 1 multiplied by, we decrease by 1 again from the previous one to be n minus 2. We decrease by 1 from the previous one to be n minus 3, multiplied by up until when the product reach 1, right? So you can see that the product always ends with 1. So there is a factorial button on your calculator, and you can get it by actually pressing shift and another button that has this thing on top. Sorry. And you just press shift and there's another button on your far right that is that x exponent minus. So you just press it and the factorial will appear. So it's very important to notice that 0 factorial is equal to 1, right? So you'll understand it as we move further, why 0 factorial is equal to 1 and why is it not maybe we start with 0 and like that, right? So just for now you have to know 0 factorial is equal to 1, and I'll explain it as we move further in this lesson. So let's look at example 1 that Kevin Smith used. It says a grade 12 learner has an accounting, science, Zulu and mathematics textbook, right? So there's an accounting, science, Zulu and mathematics textbook. How many different ways can they be arranged in a bookshelf, right? How many different ways can they be arranged in a bookshelf? So now let us look, how many items do we want to arrange? We have accounting, science, Zulu and mathematics textbook. So we have 4 different items or books that we want to arrange, right? So we can actually use the factorial notation in order to determine the number of different arrangements that can be made, right? So it's very simple. If I say I have 4 items that I want to arrange, how many different ways can I arrange those items? Simply use the factorial notation. How? Simply say, because you have 4 different items that you want to arrange, it means they can be arranged in 4 factorial ways, right? So this is the same as, okay, my pen is acting up. We said it's 4 factorial ways. So this is the same as 4 multiplied by 3, we decrease by 1. Remember, we decrease by 1, multiplied by 2, multiplied by up until when the product ends with 1, right? So that will give us, we can just press the calculator and we can get an answer. Or we can actually interpret it in this way, right? It means because we have 4 textbooks, we need 4 spaces, right? 1, 2, 3, 4. 4 spaces. So in the first space, how many choices of books can you put there? You can either put an accounting book, you can either put a science book, you can either put a Zulu book, or you can either put a mathematics book. So how many choices of books can they be placed in the first space? It's 4 choices, right? Okay, 1 book is going to sit there. Let's go to the second space. How many choices of book can be placed there? So already 1 book has seated in space 1, right? When you go to space book 2, how many books are left? 3 books, right? So we have 3 choices of books that can sit in space 2. Like that, we'll have 2 choices of books that can sit in space 3. Then we'll only have 1 choice of book that can sit in space 4. So you can see to basically be 4 multiplied by 3 multiplied by 2 multiplied by 1, which is actually the same as 4 factorial, and you can actually use a calculator to get the answer. So using a calculator, 4 times 3 is 12, times 2 is 24, times 1 is still 24. So there are 24 different ways in which these 4 books can be arranged. I hope that made sense. Okay, let us look at example 2. In how many different ways can the letters of the word Max be arranged? A repetition of the letters is not permitted, right? So they're saying a repetition of the letters is not allowed. It means if you use a letter, you don't have to use it again because you don't have to repeat. Repetition of the letters is not permitted. It's not allowed, right? Okay, let us look at the letters of the word marks. How many ways can they be arranged? So what you actually do before answering a counting principle question, you ask yourself, how many choices do I have, right? Because in counting principle, we simply multiply the number of choices or outcomes that we have in each particular situation. So how many choices do we have with the letters of the word marks? Let's count. We have M, 1, 2, 3, 4, 5. So we have 5 choices of the letters M-A-R-K-S. It's 5 choices. In how many different ways can they be arranged? We know factorial notation is going to be very simple. So we simply say, because we have 5 letters that are to be arranged, then they can be arranged in 5 factorial ways, right? So they can be arranged in 5 factorial ways. We can simply use a calculator to determine that answer. Then you'll be able to see that this it's actually very simple. So 5 factorial ways, this will give us an answer of, I think it's, let's see, it's gonna be 5 times 4 times 3 times 2 times 1, which is actually 120 different ways, right? So let us use also this understanding of this solution here. Let's see. So we have 5 letters to be arranged. It means we must have 5 spaces, right? We create 5 spaces. After creating 5 spaces, in the first space, how many choices of letters can be made? We can either put M, we can either put A, we can either put R, we can either put K, we can either put S. We have how many choices? 5 choices. Hence, it's written 5 choices. In the second space, remember, a repetition of the letters is not allowed. It means that the letter that we use here, we cannot use it in the second space. It's already in first space, finished, right? Let's go to second space. How many choices can we have? So we have already used 1 letter in space 1. So when we come to space 2, we only have how many choices? 4 choices. Remember, in counting principle, you only care about the choices that you have in each particular situation, right? And so I'm talking about the choices. So let's go to space 3. How many choices do we have? We'll be left with 3 choices, 2 choices, and 1 choice. So this is the same as 5 times 4 times 3 times 2 times 1, which can be denoted as 5 factorial, right? So it can be denoted with 5 factorial. You press your calculator, then you get an answer of 120 different choices or different letters, different ways in which you can arrange the letters of the word marks. Okay, let us look at example 3, and this is quite an interesting example from Kevin Smith's study guide. It says we have 2 different history books, and we have 3 different geography books, and we have 2 different science books. So they are placed on a bookshelf, right? So A, how many different ways can they be arranged, right? Okay, before answering that question, you ask yourself, how many choices, how many books, how many items, how many objects are there to arrange, right? It's 2 history books plus is 3 different geography books plus is 2 different science books. So in total, you have how many things that are there to be arranged? It's 7, right? So you have 7 total books that you want to arrange. 7, right? So using fundamental counting principle, in how many different ways can you arrange 7 different items? We talked about the factorial notation, right? Just now, previously, we talked about the factorial notation. We have 7 different books. In order to arrange them, simply arrange them in 7 factorial ways. So that's it. So, and 7 factorial ways will be 7 multiplied by 6 multiplied by 5 multiplied by 4. Let me just delete this. Multiplied by 3 multiplied by 2 multiplied by up until when the products end with 1. So that's it. We're just gonna use a calculator and we'll just say 7 factorial, and let's see how much will it be. So it's gonna be 5040. So there are 5040 ways in which those different books for different subjects can be arranged. B, how many ways can they be arranged if the books of the same subject must be placed together? So this is a very interesting question. And most of the students find it very challenging to answer this question because they're quite confused what's happening and all that, right? But let me just try to explain and see how it goes. So they're saying how many ways can they be arranged if the books of the same subject must be placed together, right? Okay, so I love how Kevin Smith did try to explain this. So we have history books, right? It's 2 of them. So we must have 2 spaces for the books. So they must be together. We take them as like together in the same box, right? So we also have geography books. So we have how many of them? 3 of them. So they are also in the same box. So we also have science books. So they are also in the same box, right? So how many different ways can they be arranged if the books of the same subject must be placed together, right? So if you are arranging items and you are placing them together, what you have to take in your mind is that those things, they become one thing, right? You count them as a one item, right? Because we are saying they are together. So it's like when you are going to put them, they must be together. So even if you are arranging them, it's like it's one thing, right? We count it as a single thing, right? So if we are counting it as one thing, how many ways can you arrange, right? Like, okay, so it means we have history, geography, and science. In how many ways can you arrange them if we are placing them together like that? So because we count them as one item, it's going to be 1 for history, 2 geography, 3 for science. So these ones can be arranged in 3 factorial ways, right? Because there are 3 items. So remember, we are counting those books that are together as one item. Hence, we are saying there are 3 items. We can arrange them in 3 factorial ways, right? So that's it. So let's move now. But this is not the final answer. Inside the history books, we can either place the first history book and we can place the other history book following, right? Or we can start with the other history book and then follow with the first history book, like that. So you can see that we have 2 items inside the history books. We also have to include those number of arrangements that can be made inside, right? Inside each block. So they can be arranged in 2 factorial ways because there are 2 of them there. So let's go to geography. How many items do we have? We have 3 items, right? So because it's 3 of them inside, they can be arranged in 3 factorial ways. Then let's lastly look at science books. So it's 2 of them inside, so also they can be arranged in 2 factorial ways. So this is the total number of arrangement that can be made. Let me just repeat it. If they are saying things are seated together, you take them as one item and you count how many items are there to arrange. That's the 3 factorial we got there. Then you also have to go inside and you calculate how many different arrangements can be made. The history book can be placed in this way, or they can be placed in the other way, like in the other way around. Hence we are saying 2 factorial, then geography book 3 factorial, then 2 factorial for the other book. So we're simply going to multiply those things, then we get the total answer. So it's just going to be 3 factorial, then multiply by 2 factorial, multiply by 3 factorial, multiply by 2 factorial, then the total answer will be 144 different arrangements that can be made. And Kevin Smith also explained this very much clear. So he said this means that there are two factorial ways in which the history book can be arranged inside, and there are three factorial ways that the geography books can be arranged also inside, and there are two factorial ways that the science book can be arranged inside. So you can also take into account the subject that can be arranged in any order. This means that history, geography, and science, because we have three subjects, and we are saying those books, we are taking them as one thing, then they can also be arranged in three factorial ways. Then you simply multiply those number of different arrangements that can be made in order to get the final answer. Okay, let us now go to example 4. We're still on Kevin Smith's study guide. So it says, in a school there are 8 prefects. We have 8 prefects. We have 5 girls, and we also have 3 boys, right? So they are to be seated on a stage for an assembly. How many different ways can they be seated? How many different ways can they be seated on stage? Uh, uh, yeah, that's the first question. So let us answer it A. So in answering this question, when answering a fundamental accounting principle question, what you think of is the number of choices that we have in each particular situation. So how many items are there to arrange? We have 8 people, right? So we already learned about the factorial notation, right? Factorial notation, it helps us to count the number of ways in which you can arrange different items. So because we have 8 people that are to be arranged, it's simply going to be 8 factorial. So 8 factorial, is the same as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? You can just use a calculator to get the final answer. Unfortunately, I don't have a calculator close to me, so just use a calculator, then you get the answer, right? So that's it. So B, let's go to B. How many ways can they be seated if all boys and girls are to sit next to each other? So this is an interesting question, and most of the learners find it very challenging to answer this question, because to them it sort of don't make sense, right? But it really makes sense. We're saying if all boys and all girls are to sit next to each other, how many ways can they be seated, right? So if all boys, I like how Kevin Smith did this question, approach this question. If all boys and all girls are to sit next to each other, right? So it means that we should take the girls. Okay, let me just symbolize it using G. Oh, this thing does not want to wrap. Let's see. Okay, great. So we can take the girls. We have 5 of them. 1, 2, 3, 4, 5. They have to sit next to each other, and the boys must sit next to each other. So all girls are together, all boys are together. So in how many different ways can they be arranged? Can they be seated? We said it in the previous example that if we have items together, we take it as one thing, right? You take them as like it's one thing that you are going to arrange. So now, how many items do we have? If we are taking it as one thing, we'll have how many items? 1, 2 of them, right? They can either sit in this way, or they can shift like this. The boys can start, then followed by girls. We have 2 factorial ways in which we can do that. It's going to be 2 factorial, right? So don't forget, inside, how many ways can they be arranged? How many girls do we have? 1, 2, 3, 4, 5. So inside, we have 5 items to arrange, right? They can be arranged in how many factorial? In 5 factorial ways. So also with the boys, inside, how many ways can they be arranged? We have 3 of them, so they can be arranged in 3 factorial ways. In 3 factorial ways. So in 3 factorial ways, so we can just simply use a calculator and we can get the answer of that thing. Okay, let's go to C. Or let's actually get the answer of these things, because I think they're going to be very useful in the next session. So let me see. Okay, we said 8 factorial, and it's gonna be using my calculator. It gave me 40,320 ways. It's a lot. Just imagine, just 8 people, you can arrange them in 40,320, sitting this person this side, changing this one this side, then like that. 40,320. It's a lot. Then for this one, for our number B, we said 2 factorial, 5 factorial times 3 factorial is giving me 1,440 ways, right, in which you can arrange them. Let's go to C. So if the prefects are randomly selected, what is the probability that all boys and girls being seated next to each other, right? If we just randomly select, what is the probability that all boys and all girls are seated together? So in other words, all boys together and all girls together. Find that probability that if you just randomly select the prefect there, you'll find that all boys and all girls are seated next to each other, right? So we know that the probability of an event is equals to the number of events, that is the number of favorable outcomes, divided by the number of sample space, that is the total number of sample space, or in this case we can say it's the total number of ways in which you can arrange all people. So the number of events is the number of favorable outcomes. We want to get the probability that all boys and all girls are seated next to each other. So in how many ways can we arrange all boys and all girls together? We already calculated it in number B, and we find that is 1,440 ways. That is when all boys and girls were seated next to each other, right? So the total number of sample space in this case will be the total number of ways in which you can arrange all people, and we already calculated it in A, and we got 40,320. So you can see we're just gonna use a calculator and see. So with a calculator I'm getting 0. Okay, it's actually 1 out of 20, which is 0. If we are rounding off to 2 decimal place, it will be 0.04. 0.04. So you see, there are low chances that when you just select those prefects, you'll find that all boys and all girls are seated next to each other. Okay, let us move now. We'll be dealing with repetition. We're still on Kevin Smith study guide. He says, consider the word Bob, right? In the previous example, there were 3 letters in a word. There were 3 factorial ways of arranging the letters, right? However, in all of these cases, there were no repeated letters. So just think of the previous example we did of the word Max. There were no repeating letters there, right? So we just said, because there were 5 letters, we just said 5 factorial. Also, there was another word, I think it's a 3-letter word, and there was no repetition, and we just say 3 factorial. But consider the letters of the word Bob now. In the case of the word Bob, there are places for base, and base can be swapped, right? Because you can either, which one is the first B, which one is the second B? So we have a repetition here. So remember, we are dealing with repetition, where you are given a letter and there are some words, I mean some letters are repeating. So in the case of Bob, if the places of the B's were swapped, the word will still be Bob, and it will not count as different arrangement, right? It does not count as different arrangement, even if you swap the B, it's still Bob. So In order to count for repetition of letters, we divide, because we have 3 letters in Bob, we say 3 factorial, but because we have some repeating letters, it's B that is repeating twice. So we're going to divide by 2 factorial because the letter B is repeated twice, right? So we need to cancel out that effect of repeating letters so that even when we swap, we know that we don't have a different arrangement, still the same. So in order to avoid saying just we say 3 factorial because there are 3 letters, it might be wrong. So here we are dealing with words with repeating letters. So what you do, you check this letter is repeating how many times. Is 2 times. You divide by the factorial of that, because we need to cancel out that effect of repeating letters so that our arrangement may be of different arrangements, right? Not as the same arrangement as you sub, still the same. So if the word was Bobby, right? If the word was Bobby, how many letters are there? 1, 2, 3, 4, 5, right? We're gonna say 5 factorial, then we're gonna divide by, our b's are repeating 3 times. So it means we're gonna divide by 3 factorial as the letter B has repeated 3 times, right? So that's how you do when you're dealing with repeating repetition. So let's look at the example 1. We're given the word probability. It's a long word. A. Determine the number of different ways in which the letters can be arranged, right? So how many letters are there to arrange? We have to count. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 letters, right? So in order to arrange them, it's going to be 11 factorial. But is that the answer? No. We have to check if there are some repeating letters. We're just going to divide by the factorial of those repeating letters. Okay, if you check in our letter probability, we have B's, and our B's are repeating 2 times. It means we're going to divide by 2 factorial. And we also have I's, I. And our I are repeating how many times? It's also 2 times. We also multiply by 2 factorial. And we also have what? Do we have another letter that is repeating? Let's see. No, it seems as if no letter is repeating. So that's the final answer. In order to arrange those all letters differently, it's 11 factorial divided by 2 factorial because our B is repeating twice, divided by another 2 factorial because our I is also repeating twice. So it's 11 factorial divided by 2 factorial times 2 factorial. It's a huge number. So it's giving me 9979200. So you can see that there are many different arrangements that can be made. Let's move to B. B. If the word has to start with B, with a B, how many different ways can the word be arranged? Now you are told that your word has to start with B, right? How many different ways can the word be arranged? Now look, so we're saying in the first position it must be B. So if in the first position it must be B, how many choices do you have? It's only one way you can do so. So it's one way, right? So 1B has been out. It's out because we're saying we are starting with it. It's fixed. It's out, right? So let us now look at the letters that are left. It's P, R, O. We just say that B is out. We say A, B, I, L, I, T, Y. So we have these letters that we have to arrange because we say it must start with B. So it's one way we can do so. The answer I wrote 1, right? But the remaining letters, how many ways can they be arranged? How many of them? There are 10, right? So they can be arranged in 10 factorial ways, right? But don't forget that we have to divide by the repeating letters. So in this case, we have I that is repeating 2 times. So we're just going to divide by 2 factorial, right? Because we can't say b is repeating because this b is already out there. We have to start with it. It's already out. So the remaining letters, how can they be arranged? They can be arranged in this way. So the total number of ways in which these things can be arranged, you just say 1. When it starts with b multiplied by 10 factorial over 2 factorial, then you get the answer. So it's 1 multiplied by 10 factorial over 2 factorial to give me a lot. It's 18,14400. So you can see that there are a lot of arrangements that can be made, and that's the answer. C, what is the probability that the word starts with B? So this is going to be simple also because we already calculated how many ways can we arrange if we start with B. So the probability, let me just write my C here. So the probability of an event, we know that is equals to the number of event divided by the number of sample space. That is the total number of ways in which you can arrange everything. So the number of events, we are saying the number of favorable outcome, the word must start with B, and we already calculate how many ways we can do so in B, right? So it was 18,14400. 18,14400. Just then divide by total number of ways in which you can arrange all letters, and we already calculated in number A, and we got 99,997,9,200. So we're just gonna use a calculator and get the answer of that thing. 18,14400 divided by 9,979,200. So it gives me 2 out of 11, 2 over 11. In decimal, it's going to be 0.18, rounded off to 2 decimal place. So that will be the probability that the word will start with B. Okay, let us now move to the second example. So they're saying you are given the word Mississippi. Mississippi, nice word. A, determine the number of different ways in which the letters can be arranged, right? Okay, in counting principle, what do? We count how many items are there to arrange, right? So we need to arrange the letters of the word Mississippi. So let us count how many letters are there. So this is A. Let's check. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 letters that are there to be arranged. So it's going to be 11 factorial, right? Let's see. It's 11 factorial. But don't forget, if we have some repeating letters, we have to divide by their factorial in order to cancel out the effect of those repeating letters, so that the word that can be formed, they are all different. So let's check. We have I that is repeating 1, 2, 3, 4 times. So we're going to divide by 4 factorial. Another letter that is repeating, we have S that is also repeating 1, 2, 3, 4 times. Okay. Another letter that is repeating, we have P that is repeating 2 times. So we multiply by 2 factorial. So in total, we're just going to use a calculator to get the answer of that. It's 11 factorial divided by 4 factorial, multiply by 4 factorial, multiply by 2 factorial. So the answer will be 34,650 ways in which you can arrange those letters in different ways. So you can see it's a lot. If you are doing it manually, you won't finish. Just imagine 34,650. It's a lot. It's too much. Let's go to B. If the word has to start with M, how many different ways can the word be arranged, right? You want to start with M, in the first place, how many different ways can the word be arranged? If we are starting with M, in how many ways can you do so? It's only one way. That is, you have to put M in the first place. So you have only one choice, one M. In fact, one way in order to do so. Then we focus on the number of arrangement or the remaining letters. How can they be arranged? So it will be I, we have I, S, S, I, okay, it's another S, 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 I, P, P, I. So these are the remaining letters. We have to determine how many arrangements can they be made, can they be made with these remaining letters. So we count them. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them will be 10 factorial divided by, we have some repeating letters, right? We have to divide by them. We have I that is repeating 1, 2, 3, 4. So we need to divide by 4 factorial, and we also have S that is also repeating 1, 2, 3, 4. We have to divide by 4 factorial, and we also have P that is repeating 1, 2 times. So we need to divide by 2 factorial. So that's how you do. So it's actually the same logic, the same way. So it's 10 factorial divided by 4 factorial times 4 factorial times 2 factorial. So it will be 3,150 ways in which that thing can be done. C. What is the probability that the word starts with M, right? So we know probability equals to number of favorable outcomes divided by total number of sample space. Number of favorable outcomes, number of arrangements when the letters start with M, we already calculated in B, and it was 3,150. Total number of ways in which you can arrange all letters, that is the total number of sample space, is 34,650. So it's going to be 3,150 divided by 34,650. So it's 1 over 11. 1 out of 11, which is the same as 0.09. 0.09. Okay, let us move now to example 3. They tell you a flag is to be designed using the colors yellow. We have yellow, blue, green. So these are the colors that you must use when you're designing this flag. So there are 4 slots which the colors can be placed in, as shown below in the and the color yellow has to be used twice. You can see in the diagram they use twice in the first, they use twice in the last space. So A, determine the number of different flags that can be made, right? Determine the number of different flags that can be made, right? So how many colors are supposed to be used, or how many slots, how many choices do you have? So you have 1, 2, 3, 4 slots, 4 spaces, right? So it's going to be what? 4 factorial, because you have 4 items that you have to use. 1, 2, 3, 4. You have to use 4 colors. But because the yellows are repeating, right? And we want to form different flags, right? Because the yellows are repeating twice, we're just going to divide by 2 factorial, because yellow is repeating 2 times, to cancel out the effect of the repeating yellow, so that we may have different flags. So it's 5 factorial divided by 2 factorial. It's going to be 12 different flags that can be formed. Awesome. B, how many different flags can be made that start on a yellow and end on green? So it must start on yellow, but it must end on green. So we have 4 slots, 1, 2, 3, 4. Start with yellow, and with what? With green. So if it's starting with yellow, in the first slot, it must be yellow. So it's only one way to do so, right? It must be yellow. If it's ending with green, also we only have one way in which you can do so, right? So we put 1. So the remaining color is what? It's blue and yellow, right? So in how many different ways can you arrange this? You can start with blue, then yellow, or you can start with yellow, then blue. So they can be arranged in 2 factorial ways, those 2 colors. So in total, you simply multiply out those things and you just have 2 as your final answer using your calculator, obviously. Okay, let us quickly now look at the last section, and we want to talk about selections. It's about selections. We will now use the factorial notation to deal with problems where there are a limited number of places which can be filled from a group, right? So for example, if maybe I have a group of 5 learners, but I want to see how many ways can I arrange 3 of them from those 5 learners, right? So you can see, like, we deal with limited number of places which can be filled from a group. So an illustrative example is on page 302 on your Kevin Smith study guide. If you don't have it, you can order it online. You can go to bookstores, CNN, something like that. You can go there and you can buy it, and actually you can purchase it online also. But if you have it on page 2, we dealt with an example where there is a security system that required the user security code, right? And that code consists of 4 digits, and it was seen that if repetition of digit was not allowed, there are 10 choices for the first digit. Then, because the repetition is not allowed, second choice is a second option on the second space. We have 9 choices for the second digit, 8 choices for the third digit, 7 choices for the fourth digit, and the codes of like 10 times 9 times 8 times 7, which is like this number of choices, gave us 5040. If you can still remember, we did this example when we were starting. Okay, so using factorial notation, 10 times 9 times 8 times 7 can also be written as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 6 times 5 times 4 times 3 times 2 times 1. Why? Because we know that this 6 times 5 times 4 times 3 times 2 times 1 can cancel out each other, and we'll simply be left with the same 10 times 9 times 8 times 7. And this can also be written as, let's look properly for you to understand how do we deal with this thing. It's actually called permutation. This is actually called permutation, in which we want to arrange different items. We want to calculate how we can do it. So this is the same as writing 10 factorial. This one, remember, this one is the same as, if we're multiplying till 1 is 10 factorial, that one till 1 is also 6 factorial. So in this example, there were 4 spaces to fill out 10 choices, which can be seen in this example. That the general rule for this type of situation, if you want to arrange certain items from a group of items, so you can actually say, if we have r spaces to be filled from n different choices, from n choices we have r spaces that we want to arrange or that we want to fill, so the number of possible arrangement will simply be n factorial divided by, so I said it will simply be on the previous one, right? It will simply be n factorial divided by n minus r factorial. So we use this formula in order to arrange certain items from a group of certain items, or in order to fill out those spaces from a group of certain items. You just say n item, how many items are there, how many people do I want to arrange from those groups, then just use that formula. So this is your formula for permutation. You can use it to do so. So let's look at example 1. There are 12 contestants. This word, In a race, how many different ways can the first, second, and third place be arranged, right? You have 10 contestants, but you want to see how many different ways can the first, second, and third place be arranged. So you simply use this formula. You have 10 of them, but you want to see in how many ways can you arrange the first one, second, and third only, right? So you simply say 12 factorial divided by 12 minus 3. So the 3 is for the 12 of for the 3 of them, first, second, and third, that are to be arranged. So there are 3 places that are need to be filled from 12 choices. So you say 12 factorial divided by 12 minus 3 factorial, then you use your calculator and you get that answer. Simple, 1320. So let's look at example 2. A local running club is holding a fundraising lottery. 4 numbers are to be drawn from a possible 10 numbers. You see, so you must know how many things are to be arranged from how many items. So our N here is 10 because we are drawing from 10 numbers, but we need 4 numbers. In order for a ticket to win, the numbers on the lottery sheet must be in the same order that they are drawn. How many different winning arrangements are possible? So we need to arrange what? We need to see how many ways in which you can draw out those 4 possible winning numbers from how many? From 10 total numbers. So you simply use that formula. You just say 10 factorial divided by 10 minus 4 factorial, then you get the answer, because we need four spaces that need to be filled, right, with those numbers. So that's a 10 factorial divided by 10 minus 4 factorial. You use the formula, then you get the answer. It will be 5040. Okay, so this marks the end of our lesson. Thank you very much for joining us today. Don't forget to subscribe. If you are new to this channel, don't forget to subscribe. And yeah, let's meet next time. Thank you.